In this video, we will show a backward-facing step to show the features of TransAT. A backward-facing step is an interesting problem that can show recirculation and vortices within a flow. We have air entering in the left domain with a velocity of 0.1 meters per second in the u direction. On the right side of the domain, we have a pressure outflow condition. Our geometry retains small dimensions so that we can ignore turbulence. The dimensions of our problem are as follows. We have a 50 millimeter length in the x direction and an inlet area of 5 millimeters by 10 millimeters. The backward step is 35 millimeters from the outlet and is 5 millimeters in height. Through this tutorial, we will learn the following things. We will learn how to create a domain by setting up a mesh, defining blocks, and adding boundary conditions. We will define inputs of model and material parameters, initial conditions, and simulation controls. Once we have run the simulation, we will post-process our results with peer review. To begin TransAT, navigate to the shortcut on your desktop or alternatively on Linux with the command transatui.py. With TransAT open, we will create a new project. Remember, each project should be saved in a unique directory so that files do not conflict with each other. We'll make a new folder. And define a name for our project. Once TransAT is opened, we're first brought to the Mesh tab. There's additionally a Geometry tab for defining objects in the flow domain, a Mesh for defining the domain and boundary conditions, Input for defining model parameters, and an Execute tab for running the simulation. We'll define the domain and grid as per our problem setup, with an x min location of 0 meters and x max of 50 millimeters. We'll define the y and z coordinates as accordingly. Once we have the dimension set up, we can define cells for our problem. We'll define the discretization for our cells, which is 1 plus the number of cells we want. For our problem, we would like 100 cells in the x direction, 50 cells in the y direction, and 10 cells in the z direction. Notice that there's a cell ratio, which defines a growth parameter. Because we're not using any sort of refinement for our cells, we do not need to set any value here. Next, we'll define some blocks. Our blocks can be used to run a simulation on multiple processors, as well as to define a geometry for our flow. In this case, the blocks will be used for our geometry. We'll be subtracting a block to create our backward step. We want 4 blocks, so we'll discretize it by 2 in the x direction and 2 in the y direction, splitting it into 4 blocks. Now, if we rotate, just to get a better view, and we delete the first block, we see that we are close to our backward step geometry. We just need to define the backward step to 35 millimeters away from the outlet. We'll do that with the Modify Block button. We'll change this to 15 millimeters from the inlet. And we'll repeat this process for the remaining 2 blocks. But instead, the x min value will be adjusted to 15 millimeters. With the mesh and blocks defined, we can now set our boundary conditions. We will have 3 boundary conditions for our geometry: an inlet, a wall, and an outlet. We'll set those names. And adjust the types accordingly. And finally, change the properties for our boundary conditions. For our inlet, we want a velocity-based inlet with a constant value of 0.1 meters per second in the u direction. For our outlet, we want a pressure-defined boundary condition of 0 pascals. For our wall boundary condition, we can leave the default values. Now we need to assign our boundary conditions to surfaces. For our x min 0 will be our inlet, and we'll use the assign boundary condition button. Our x max 0 will be our outlet, and the remaining x and y surfaces will be walls. We'll notice that the z boundary conditions are left undefined. By default, this leaves them as symmetry boundary conditions, as we desire for our problem. With our boundary conditions and domain set up, we'll save our project using Files and Save. With our domain and boundary conditions defined, we can set up our physical models under the Input tab. Under basic equations, we'll be solving for pressure, U, V, and W velocity. Under reference properties, we can define some reference parameters. These are not used in simulation calculations, but just to define non-dimensional numbers. And we'll use a reference length of 5 millimeters. We won't be modeling turbulence or any other advanced models. Under our phase properties, we'll ensure that air has been loaded from the material library, and we can next move on to simulation parameters. We'll be running a steady simulation for a maximum of 800 iterations. Under advanced options, we can change the relaxation parameter to 0.9. This will help to speed up the simulation, but must be used with caution as it can lead to an unstable simulation. Under equations, we'll ensure that the convergence tolerance is set to 1 e to the negative 6. Under advanced solver options, we can change pressure to GMRES, or for now, we'll just leave it how it is. Next, we'll set up the initial conditions. For our U velocity, we'll initialize the entire domain with 0.1 meters per second. All remaining variables will be left at 0 throughout the entire domain. Under our output management, we can ensure that pair view will be the type of output file every 100 iterations, that the output variables being plotted are pressure, U, V, and W velocity, and that non-dimensional numbers will be calculated. This is just used to help gauge the simulation. Finally, we are ready to execute the simulation. It is possible to increase the number of processors as long as we do not exceed the number of blocks that we have. We can use 1, or for a little bit faster simulation, 2 processors. And we'll let the simulation run. With the TransAT simulation and results fully converged, we can now open up pair view. We'll need to load the results from the directory that they were saved in, and look for the VTM file, which contains the pair view results. We'll apply this and wait for the results to load. First, we have an outline of the 3D geometry loaded. We can change this and view a surface and change the coloring to any of the variables we output. What we are interested in this tutorial is creating a slice through the center of the geometry. We'll do that by using the slice button. We'll define it in the Z normal direction and confirm that it is at about 5 millimeters in the Z direction, or halfway through the geometry. We'll hide the plane and apply. First, a cool to warm color map is plotted. We can change this on the right with the color map editor. Loading a preset, let's change it from cool to warm to blue to red rainbow. Additionally, we can change values in the label. To do so, click on the label editor button and change the name to U velocity, for example. Additionally, we can change the precision and the formatting of the label. Now, we want to plot some arrows of velocity onto our slice. To do so, we'll select the backward step in the model tree and create a calculator to calculate a velocity magnitude. In our function, we need to define u times I hat plus v times j hat. With calculator selected in the model tree, we'll create a glyph, and we'll change the glyph type from arrow to 2D glyph. We'll make sure the vector result is the attribute, and we'll change the scale mode to vector, and click apply. Now we'll need to change the coloring to solid color so we can better see the arrows. One last part of the tutorial will be to show how to create stream tracers. We'll hide the glyphs and the calculator. Selecting calculator from the model tree, we'll create the stream tracer. From a high resolution line source, we'll change the seed type to a point source. Any stream tracers that pass through this sphere will be plotted in our paraview. So we'll apply, and we'll hide the slice. We can again turn back on the backward step results and change it to an outline so we get a better idea of where the stream tracers pass through. Changing the movement type from 2D to 3D and zooming in on the results, we can view the stream tracers. Thank you. I hope you enjoyed this tutorial, and I hope you can begin quickly using TransAT.